Welcome back. This video lecture is about the measurement of high impulse currents using Rogowski's coil and the rarely used magnetic links. Coming to the Rogowski's coil, already or also known as a magnetic potentiometer. The operating principle is very simple. As you all know, if a coil is placed surrounding a current carrying conductor, a voltage signal will be induced in the coil, or what you call it as an EMF will be generated by the coil, in the coil, which is just like your voltage signal. And if you are going to measure that one, this voltage signal is proportional to the linkage phenomenon and also the amount of current which is flowing. So, this particular principle is utilized for the measurement of high impulse currents. See the operating principle. If a coil is placed surrounding a current carrying conductor, the voltage signal induced in the coil is Vi of t is equal to M into d by dt of it, where M is a mutual inductance between the conductor and the coil and I of t is the current flowing in the conductor. This is the figure, see here. This is the current carrying conductor which is carrying a current of I of t. So, this current, it develops a magnetic field around it. See, I am placing a coil around this one. Because of this magnetic field, EMF is being induced in this coil because of the magnetic flux linkages. These are linking this coil. So, this is the principle of mutual inductance. Because of the mutual inductance, I am having an EMF which is being generated here, which is Vi, induced voltage. So, Vi of t is proportional to M and also I of t. As you all know, Vi of t is equal to M into di of t by dt. This induced voltage is transmitted through a coaxial cable and then thereby it is measured with the help of some instrument here, Vm of t. Now, see here. The coil is wound on a non-magnetic former of toroidal shape and is coaxially placed surrounding the current carrying conductor. Now see here, the coil is wound on a non-magnetic former of toroidal shape and is coaxially placed surrounding the current carrying conductor. See, this is the current carrying conductor coaxially placed around the conductor, toroidal shape, the coil is coaxially placed. The number of turns on the coil is chosen to be so large to get enough signal induced. You know that mutual inductance is basically proportional to the number of turns of your coil. So, more number of turns, more inductance, so more amount of voltage you will be getting for measurement. So, higher number of turns is to be chosen and the coil is wound crosswise. This is generally done to avoid the leakage inductances. So, the coil is wound crosswise to reduce the leakage inductance and an integrating circuit is employed to get the output signal voltage proportional to the current to be measured. See, this is an integrating circuit RC. So, why I am using RC, that we will see now. So, this is induced voltage M into di by dt transmitted through cable, terminated through some resistance to avoid reflections, and this again is passed through RC network, an integrating network. Now, see here. So, Vm of t, now see here, this is Vm of t. So, this is assuming that this is Vi of t here. Vm of t is nothing but integral of this Vi of t, whatever the voltage which is being induced. See, Vm of t is 1 by Rc integral of Vi of t. You know what is Vi of t already, M into di by dt. So, integral differential get cancelled. So, what you will get? Vm of t is nothing but M by Cr into I of t. So that's why I am utilizing a RC integrating network. So Vm of t is equal to m CR into I of t. So if you want to have I of t, you just transfer these elements to here. This is the simple principle of your Rogowski's coil. Advantages. It can respond to very fast charging currents because of its low value of inductance. So even if the rise time is somewhere around 10 to the power of minus 9 seconds also, it can easily measure. And since I am not utilizing any iron core, I am just going for the air core. So there is no question of saturation or linearization or non-linearization. So my measurements will be highly linear. And the most important thing, it is lower construction cost and smaller size when compared to the conventional series. I just use a coil and I am just using a coaxial cable ended with resistance, and I am utilizing an integrating network. And there is no much requirement of temperature compensation also. So it has good advantages, but the limitations. I do require an integrator circuit, an RC properly designed integrator circuit, and make sure that it doesn't alternate the signals. So I do require an additional integrator circuit, and at frequencies beyond 100 megahertz, it will be difficult for me to measure the impulse currents because of the skin effects which are offered by these conductors. So it is suitable for frequencies less than 100 megahertz. So that's all about Rogowski's coil. We start with the principle of operation, and we have gone this equation derivation and the important components. A quick review of the important components. This is your main conductor, this is your coil, this is your coaxial cable, this is your terminating resistance and an integrator. So once again, this is your main current which is to be measured passing through your conductor. A coil for inducing your EMF. This is coaxial cable for transmitting the analog signal. This is your limiting resistance, because this cable, if it is limited by your resistance, then there will be no proper reflections. So, and here if you carefully see, this is your integrating circuit. So these are the important components. You can write the working components and you can write the equation along with the advantages and limitations. And next, there is another magnetic measurement of your impulse currents, which is called as a magnetic link, which is nowadays very rarely used. In olden days, we used to use this magnetic links. These are high retentivity steel strips, which are arranged on a circular wheel or a drum. So these strips are chosen such that they do have a remanent magnetism for current pulses. So whenever you do have a current carrying conductor, let us suppose this is your current carrying conductor, your magnetic links will be placed. This is your current carrying conductor. Magnetic links will be placed here, 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 here. So because of your current which is flowing in your current carrying conductor, if I am placing my strips parallel to this one at some known distance. So because of this, here what will be happening? There will be some sort of magnetism, remanent magnetism will be developed in your steel strip. So if there is a current rise, there will be a remanent magnetism which will be developed. Now after some time, when I want to measure, I will take down this steel strip, I will take this one to the laboratory and I will measure the remanent magnetism. So this remanent magnetism gives a measure of what is the amount of current which is flowing in this conductor. So very simple concept. A conductor, a steel strip of special property which can have high retentivity. So this placed near one, if there is an impulse current, magnetism will be developed here, the same will be measured in the laboratory. So these are useful for field measurements, mainly for estimating the lightning currents on the transmission lines or transmission towers. They don't cost us much, but they may not be so accurate like the other measurements. So that's it. These are the two magnetic measurements which are basically employed for the measurement of high impulse currents. So a small recap. Hall generators are used for the measurement of high DC currents. For measurement of high AC power frequency currents, we use current transformers with electro-optical signal converter techniques. But whereas for impulse currents, we do employ magnetic measurements. We don't touch these instruments in this magnetic measurements. We go with the isolation, electrical isolation. We do use the Rogowski's coil, also called as magnetopotentiometer, and we also use the magnetic links. So that's all for this presentation. And coming to the assignments, take your time to explain the different methods of high current measurements with their merits and demerits, which I have studied here. And if it is possible, you go with the design of Rogowski's coil. Thank you. In the next lecture, we will see a modified resistive shunts for the measurement of impulse currents. Thank you.